Today we're going to look at section 5C, talking about statistical tables and graphs. And as you probably are fully aware, graphs can range from very simple to very complex. Things that you'll need to be able to pick up from this section is looking at a graph, can you answer questions associated with that graph? Can you read it, interpret it, pick out important pieces about it? And then also, it's also going to be important that we note common things that can be done to graphs to make them misleading, and so we want to try to avoid those things. But I've got a couple of examples in the back of this lesson, just sort of pinpointing some of those issues that you can see sometimes. So as you recall, in the previous section we talked about quantitative versus qualitative data. And remember, qualitative is just describing your data versus quantitative is something that's measurable or countable, so it's your numerical data. So here in example 1, it says, well, brand names of shoes in a survey, since that is, the brand names would be like Nike, Adidas, and so on. Those would be describing your data, so I would call that qualitative data. Whereas section B here, the height of those NBA players, that would certainly be quantitative data, because I would have numbers there. It's 6'2", 6'3", so on. Okay. I revisited that topic because sometimes the type of data that you have then sort of leans you in a direction of which graph that you should particularly use. So for example, bar graphs and pie charts are commonly used to display qualitative data, versus histograms and line charts are best for numerical data, that quantitative data. Just can sort of show you how your data goes up and down. It's not to say that that's the end all be all, that's the way it has to be, but it's a common way of displaying the data. Let's focus here on our bar graphs. With your bar graph here, you can see that this is data representing folks' grades, and you can see the grades on scale down below, A through F. On the left-hand side, it's the frequency of that grade. So for example, I would say that those that got an A, there would be 4 students. Those that got a B, 7 students. Those that got a C would be 9. Those that got a D, about 3 students. And for an F would be 2 students. In part A, I want to know how many students have a grade of C or better. So these are common questions that we want you to be able to, look at a graph. Can you pick these pieces out? So hopefully it's very straightforward. And I forgot to mention, over on the right-hand side, they gave us a relative frequency. We'll talk more about that in just a moment. So how many got a C or better? A C or better then would be getting a grade C, B, or A. So we just go through and we would add the 4 plus the 7 plus the 9. And if you did that, you would find that we're talking about 20 students. We want to know then, okay, in part B, how many students are in the class? Well, that would just be to go through and add all these numbers here in blue that I have already, that I've written down. Well, if we know these first 3 here are 20 and then add 5 more, we're talking about 25 students. In part C, it wants to know, well, what percentage of the students have less than a C in the class? Well, if you have less than a C, then that means you had a D or an F. I'm going to show you 2 ways here. They already have the percentages here for us, so you can see that a grade of D represents 12% of the class, a grade of F represents 8% of the class. Hopefully you could surmise then, if I want those that get a D or an F, I could just take that 12% plus the 8% and get 20%. So 20% of the class has a grade less than a C, basically a D or an F. And it should be noted that you could have easily found these percentages yourself. If you remember from our last section, we had that formula, part equals percent times whole. Let's see if I've got some room that I can write a little bit more. For our part equals percent times whole from our last unit, if we were thinking about here in part C that the number of students who got a grade less than a C, that'd be 5 students. I don't know the percentage, that's what I'm trying to find, and then the whole would be the total number of students in the class. In this case, we already know that's 25 students. Like we did in the last unit, divide by the number beside your letter, so divide by 25. And then because you're trying to find the percentage, you're going to take that 5 divided by 25, and you'll ultimately multiply that by 100, and sure enough, you're going to find out that that turns into 20%. So essentially, I've actually just already answered part D, because it says, well, how were these percentages calculated? They were calculated using this formula, your part equals percent times whole. Important features about graphs, always make sure that, if you were to open up a magazine and you see a graph, you don't know anything about it, you won't be able to interpret it if it doesn't have a title, if it's not clearly labeled. So those are really important features, to make sure that if you ever had to create a graph that you include those things. Uniform increments are also important, because if you start counting by fives and, oh, I ran out of room, so let me start counting by 25s, it really distorts your graph quite considerably. Definitely something you want to avoid. A key or legend. Sometimes those are, if you have some sort of graphic in there that you need to say, okay, well, this graphic stands for 5 fish. You got a fish there, well, that represents 5 fish, not just 1 fish, something like that. Pie charts is also important that, with those, that you have a percentage associated with each of those wedges, so that it can clearly be identified. And also has some sort of color coding or a label. If it's color coded, then that goes back to the legend that pink stands for this and blue stands for something else, and so on. All right, I'm going to flip it on over. I think that the solutions key will be able to, after I've just gone through that bar graph, I think you'll find this very straightforward. It's just talking about a pie chart, being able to answer questions associated with that pie chart, and then a histogram about NBA players. I think that, like I said, I think those will be very straightforward for you. So I will scoot on over to the next page, which is a line chart. What I did here with my line chart is I just used an example from the previous page, and I just superimposed the line chart itself on top of the bar graph. So, you can just imagine if that bar graph was just completely eliminated. But sometimes you will see a line graph on top of the bar graph. A feature that I will draw your attention to, a minute ago I said, well, your increments needed to be uniform. Notice here that you have this little symbol. That symbol there is used to show a break. That if you'll notice that the distance from the origin to this unit is 72. But for everywhere else, it's just 3 units. So this one is 72 units, and all of these are 3 units away from one another. So in order to show that there is a, you always need to indicate if you're not being uniform in some way or another, and so that's why we use the double break like that. Or sometimes you may see on a graph use what I call a heartbeat symbol. So like say you're going to go 5, and then we'll start counting by 6, 7, and so what I could do then is insert, like I call it, a little heartbeat symbol. So use either symbol that you like, two dash lines there, or like I said, a heartbeat symbol. Both of those mean the same thing. It's just trying to illustrate that, hey, we recognize our graph isn't perfect, but we're showing you, okay, we're not trying to mislead you. We're saying, okay, there's a break there. Let's see, I move on down to example 5. I think this one's worth going through, so we'll look at it. All examples are worth going through, but I think I'll definitely revisit this one, because this one is a nice throwback to our previous units. I don't want you to forget things. This is the number of animals at a local zoo, tracking them from 1999 to 2003, and then obviously tabulating the animals in the hundreds over on the y-axis, your vertical axis. So I want to find the absolute change. Remember your absolute change formula from your previous unit? That's just your new minus your old. So I want to find the absolute change from the number of animals from 2002 to 2003. So what I would do is, okay, let's go up here. 2002, right at 600 animals. And 2003 would be right at 400 animals. I want to write a sentence to figure out, okay, I want to figure out what this absolute change is, and then put a sentence to the meaning of that. So my absolute change is my new amount minus my old amount. So my new amount would be the newest point in time. So the newest point in time would be 2003. So that would be 400 minus my older time frame, 2002, which would be 600 animals, and then obviously 400 minus 600 would give you a negative 200. So then we want to say, okay, well, what does this mean? And so what that would mean then, and instead of writing this out, I'm just going to say it here. It says, I would say that the zoo lost, because of the negative sign, the zoo lost 200 animals from 2002 to 2003. Okay. Relative change, if you recall from our previous unit, is just that percentage. We'll do new minus old divided by our old. But notice here I am looking at two different years. So instead of 2002 and 2003, I'm looking at now 2000. And in 2000, from the graph, you can see that there were 300 animals at that time. And in 2001, it had gone up to 500 animals. Let's find this relative change. So the new amount would be 500 animals. So just there we go. 500 minus the old amount of 300 divided by that old. I would go ahead and say, okay, well that's 200 divided by 300. I'll multiply by 100. I'm trying to find a percentage. And if I do some rounding, that'll be, we can do that, maybe let's say 66.7%. And so to put this into context, then what we're saying here is that the zoo's animal population increased, because this percentage is positive, increased by 66.7% from 2000 to 2001. All right. And then we'll flip over to our last page. The last type of graph that we'll have here in this section is called a time series graph. And in a time series graph, time always goes on the horizontal, which is also known as your x-axis. We describe time series graphs by looking for overall patterns. And looking for striking deviations from that pattern. And you can see in both of these examples that I have up here, time is on my horizontal x-axis. And here in the graph on the left, you're looking at a Trulia property listing from April 16th, 2014 through May 7th, 2014. So just looking at a 4-week span of how property prices have increased. And hopefully you're kind of already noticing some issues with this graph, especially what's going on here on the y-axis. And then the graph on the right is looking at years from 2000 to 2012, and then estimated spending, 600 to 900 on the y-axis. And again, there's some issues with that graph as well. We'll talk about here in just a moment. Sometimes whenever you might, if you were to see those graphs online, which is where I pulled them from, you might say, hey, they're pretty straightforward, I sort of get it. But if you just sort of look at it, a half a second longer, like I said, I'm hoping that you're seeing some of the problems associated with that graph. So the graph on the left, I'm hoping that you're picking up the fact that the scale of this y-axis definitely doesn't need to be so repetitive. I don't need 153,000 and then another 153,000. Likewise for the 154. Essentially what they're doing there is, by being repetitive like that, they're trying to show you that home prices are selling. You can list your house for, they're going up, and it's kind of making it look like, hey, there's, this has got a huge spike here. We better get in on this while it's, while the getting's good kind of thing. But essentially, 153,000 to 154,000 isn't that big of an increase. So, but the way the scaling has been done here, it's been shown to do that. Another issue with this graph is that it is not equally spaced here on this y-axis, and that's also another issue. The graph over on the right, our spending, a big problem that I see with it, it says estimated spending. We don't know, whenever you see here, 2000 being a little over $850, that $850 a week, a month, it's not telling us, the units of that spending. Obviously in 2000, obviously it's a year, but we don't know if that's $850 per month that year or per week that year. What are we referring to there? Let's see, a couple other things going on in this graph. We don't know what type of spending is being, what they were looking at. Is it normal bills, or is this excess spending, that sort of thing. Um, Likewise, if you'll notice along the x-axis in both of these graphs, that heartbeat symbol, the brokenness, from the origin to here is 2,000 years, but after that it's just 1 year. And likewise, they're just starting this graph at April 16th. So um, we should definitely want to include that heartbeat symbol like I showed before, or the dashed line to show that there is a time break there. So anyway, that should conclude this section.